Hi everyone, and welcome to an additional virtual chemistry lesson for the Swedish Chemistry 1 course. Primarily aimed to you PDP students out there, but of course anyone else who wants to learn chemistry is welcome to watch the video. In this video I will talk about redox reactions, and I will have a focus on the concept of oxidation numbers. If you did not watch the previous video where I went through, for example, the definitions of reduction and oxidation, I recommend that you watch that video before you go into that one, because in this video I assume that you have some prior knowledge about these concepts. So let's have at it, so to say. So the picture that I started with, and I still have here in the lower right corner, shows what happens if we drop concentrated hydrochloric acid onto iron powder. It starts to bubble, which we in chemistry say we have evolution of gas, so it's gas evolution. And the formula for this chemical reaction, many of you probably know that when a metal and an acid react with each other, they form hydrogen gas and a salt. What will be left once we remove the hydrogens from HCl and form H2 gas will be chloride combined with iron, and that in turn will form iron chloride like this. Alright, so based on your previous knowledge, you know that, well, iron turns from iron as an element to iron as an ion, because this is a metal and a non-metal in a compound. So this is an ionic compound, and if you have iron in a compound like this, then you know that it will be Fe2+, right? Because even though it's a transition metal and don't quite follow all the rules we like, you still know that the chloride ion is -1. If we need 2 of those, that's 2 negative charges for every iron. So that will be a +2 iron ion. So now we can sort of figure out, but what happens in the HCl molecule? That's a molecule, and it's converted partly to the H2 molecule. So here we don't have any nice clear ions, we have covalent bonding instead. So in order to get into exactly what happens within molecules when we deal with reduction and oxidation, we need the concept of oxidation number. So we will get back to this chemical reaction in just a moment. Oxidation numbers is a way for us to keep track of how oxidized or reduced a substance is. It's a relative measure, so it can be more oxidized in relation to something else. It's not translatable to the number of valence electrons, and I will show you exactly what I mean by this further in the video. But if you know the oxidation number, that doesn't directly correspond to valence electrons in any way. You need to memorize a couple of rules here, okay? You need to memorize that during an oxidation, the oxidation number increases. It goes from a small value to a higher value, or maybe it will go from a negative value to a positive value. During a reduction, the oxidation number will then decrease because it's the opposite process. So I'd like you to write these down and memorize them, because we need to use these rules to solve chemical problems. And on the topic of rules, oxidation numbers is a part of chemistry where you just need to memorize quite a bit of things. But once you've done that work, once you've done that, you put in the time to memorize this, then you can use it to solve way more chemical problems than you could before. So it's worth it. First and foremost, you need to memorize that the oxidation number for an element in its natural state is given the value 0. So the oxidation number for an element in its natural state is 0. For example, iron atoms, well, they will be as pure iron, so that will be 0. You know that you have the diatomic elements as well, like hydrogen gas and oxygen gas. These will also have the oxidation number of 0 because this is their elemental form. So whenever we have them in their elemental form, the oxidation number they're given is 0. Okay. The sum of oxidation numbers of an uncharged compound is 0. Here's some compounds. You have sodium chloride, which is an ionic compound, but the sum of the oxidation number of sodium and chloride will be 0. The water molecule, well, it's a molecule, it's a compound. The sum of the oxidation numbers for hydrogen and oxygen will be 0. Here you have glucose, and the sum of all of the oxidation numbers of all these atoms will be 0. So you need to memorize that. When you look at ions in any form, the sum of oxidation numbers will be its charge. For example, the oxide ion, O2-, has an oxidation number of -2. The sulfate ion, which is a polyatomic ion, the sum of all of the atoms within the sulfate ion will also be -2, if you remember the charge of that ion. So these are things we need to know and apply. All right. Finally, and this is maybe, well, it's definitely as useful, if not more, than the other rules. Some elements have the same oxidation number in most compounds they will form. So since they pretty much always have the same oxidation numbers, we can make assumptions that they're bound to have that in new compounds we encounter. And the most common case is that their charge will be their oxidation number. But I want you to memorize a few elements and their oxidation numbers in compounds. Here. So, and I would like to put an emphasis on this, that this is the element in compounds. So actually, hold on. So now I fixed it. So, and I'm just gonna double check, excuse me. Yeah, we're still recording. So I'm doing this in one single take, so you'll have to excuse that. So some elements have the same oxidation number in most compounds, and I'd like you to memorize the following. Whenever we find hydrogen in a compound, its oxidation number is +1. Whenever you find sodium or potassium in a compound, the oxidation number will be +1. Whenever you find, like fluoride and chloride, or fluorine and chlorine, the oxidation numbers will be -1 when they're in a compound. And if you find oxygen in a compound, for example in like water, the oxidation number for oxygen will be -2. And keep in mind that we find hydrogen and oxygen in pretty much, well, in the vast majority of molecules we look at. So if we know these two, we're going to get quite far. There are some exceptions. For example, if hydrogen forms a compound with metals, then it will have the oxidation number -1. Then we call these compounds for hydrides of metals, so hydrides of metals. Oxygen can in a few cases have -1 as oxidation number in peroxides, for example, and in the compound of oxygen difluoride it will have +2. And dependent on how we combine chlorine with oxygen and fluorine, chlorine can have a different charge as well. But these are exceptions, and we won't be working much with those during this course. So, these rules can now be used to figure out if a substance is oxidized or reduced. So I'm going to go through a couple of examples, because that's pretty much how you have to learn this. You can memorize the rules, but how to apply them, well, you need to see a few examples. So that's what I'm going to do. Let's go back to the example we had before, where we had hydrogen gas being formed after hydrochloric acid and iron was mixed. You have the formula here. I like to write the formula in my notes. Then I like to write a little ON like that, as you can see over here, which is short for oxidation number, because we're going to keep track of oxidation numbers for different atoms here, okay? So, one of the rules we know is that elements in their natural state has an oxidation number of 0. So, in this chemical reaction, we have two elements in the natural state. We have iron as pure iron. We have hydrogen gas as pure hydrogen gas, which is how we find hydrogen in nature. So, then we assign oxidation numbers. Every iron atom will have the oxidation number of 0, and every hydrogen atom here will have the oxidation number of 0. 0 times 2 is still 0, so this is for all of it. The sum of oxidation numbers of an ion is its charge, right? So, if you go back here and you see the iron chloride is an ionic compound, you know that each of the chloride ions has a -1 charge, so that will be the oxidation number. And since we have two of them, we can take 2 times that. And the iron then will have a +2 as an oxidation number, because it forms a 2+ ion. So the same number as the charge here for all of these ions. The sum of this, if you remember, the sum of all the oxidation numbers in an uncharged compound is 0. So this needs to add up to 0. So 2 times -1 is -2. If we add -2 together with +2, it's 0. So this all fits the bill, so to speak. You know that hydrogen typically forms compounds, and in that case, the oxidation number will be +1, right? This is hydrogen as its elemental form, so we don't bother about this. But here you have hydrogen within a compound, right? Interesting. So the hydrogen here will have a +1. The sum of oxidation numbers in a compound equals the compound's charge. In this case, the total charge of this compound is 0. There's no plus or minus here. So then we need to match up this +1 with something that causes it to end up as 0. So then we need to put a -1 there. The sum of this will be 0. So, using the rules we've now assigned oxidation numbers to the atoms here, even within the compounds. So, how does this help us? Well, you see that iron here, it goes from a oxidation number of 0 to an oxidation number of +2. That means we have an increase in oxidation number, which corresponds to an oxidation process. So the iron in this chemical reaction is oxidized. Hydrogen. Well, we have hydrogen within this compound here. It has the oxidation number of +1. But then it's going to go from +1 to 0. So it's reduced because we have a decrease in oxidation number, according to the rules that you were supposed to memorize. You see here that with the chloride here, or chlorine atoms, they still have the same oxidation number before and after. Each atom here will have a -1, and each atom here will have a -1. So it's not oxidized nor reduced in this chemical reaction. So it sort of tags along. And if iron is oxidized, well, then it seems like iron needs to get rid of electrons based on our previous definitions. And what's going to take up the electrons is the hydrogen. So we can do it like this. This iron atom will donate 2 electrons to 2 hydrogen atoms. Each hydrogen atom will then take up 1, cancelling out the +1 charge here, which means that both of them will have 0 at the end. So that's how the electrons are transferred in this chemical reaction. And that's an example of how we can use our rules about oxidation numbers to figure out quite a lot about the chemical reaction. Let's take another example. What oxidation number does the carbon in carbonate have? Well, you're supposed to know by heart the formula and charge of the carbonate ion, which is CO3 2-. Then we can apply a few rules here to figure this out. Well, first and foremost, the sum of oxidation numbers of an ion equal its charge. In this case, the sum of oxidation numbers then must be 2- or -2. Oxygen typically forms or typically has the oxidation number of -2 in compounds. So this is a way you could do it, at least in the beginning when you're new to this. You know that carbonate consists of 1 carbon and 3 oxygen atoms. So if you write them separately like this, then we can assign numbers for each of them and then sum it all up. And this I saw another teacher doing virtual chemistry lessons do, and I thought it was a good idea. So I saw that in a Magnus Ehinger movie. All right. The oxidation numbers here, well, carbon is what we want to find out, so let's assign that the value of X. Each oxygen has a -2 here, and there's supposed to be a parenthesis here as well. So let me see if I can fix that. So here we go. So the oxidation numbers is -2 for all of the oxygens here. I put the parenthesis around them when I sum them up because I think that's easier. Feel free to do what you want. But so X plus all of these -2 equals -2. We can rewrite this as a formula. X plus -6 equals -2. Therefore, X must be +4. So that means that the oxidation number of carbon in carbonate is 4. So, another example. Let's figure out what's oxidized and what's reduced when lithium is put in water. This is a formula that I hope you know. In the beginning of the chemistry course, we talked about the alkali metals and how they behave when you put them in water. They will react with the water to form a base, that's why we call them alkali metals. So they will form hydroxides, and hydrogen gas will be produced. So here you have the formula for that happening. So let's use our rules for oxidation numbers here to figure out what's oxidized and what's reduced. We write the ON up over the reaction like this. And then we remember that elements in their natural state, they have the oxidation number of 0. In this reaction, we have lithium as pure lithium metal. And we have the hydrogen gas, which is the natural state of hydrogen as an element. We give them the oxidation number 0. You know that the sum of oxidation numbers for an ion is the charge, right? Here you have lithium ions, because you know this is an ionic compound because it has both metal and non-metals. Lithium follows our rules, so it will have a +1 charge because it only donates 1 valence electron, like so. You know that oxygen typically has the oxidation number of -2, and hydrogen typically has the oxidation number of +1 in compounds. So we have that in a few places here. We have the water molecule and we have the OH, the hydroxide ions here. So let's fill that in. This oxygen has a -2, this hydrogen has a +1. Note that the sum is 0. Over here we have 2 hydrogens. Each hydrogen has +1. So the total positive charge here will be, or not charge, but the total in oxidation numbers for hydrogen is +2. The oxidation number for oxygen is -2. So these will all cancel out as well, and we have a total oxidation number of 0 here. All right, that should be every single atom accounted for using our rules. So where do we have an oxidation and where do we have a reduction? First and foremost, lithium goes from 0 to +1. That's an increase. So that will be an oxidation, as we know. The hydrogen will go from a +1 per atom to 0 per atom. That's a decrease. We go from a positive value to 0. So that will be a reduction. All right. Let's look at another example, and I think you'll find this interesting. What is oxidized during the combustion of methane? And I can see that the title up there isn't perfect. So, what is oxidized during the combustion of methane? Thank you for your patience. Well, we write the formula. We need to have a balanced formula, of course. Otherwise, if we do calculations on this later, we will get incorrect values. We write the ON to indicate oxidation numbers. And then we start using our rules to assign oxidation numbers to each and every single atom here. So, you know that elements in their natural state have the oxidation number of 0. Well, here you have oxygen gas, so we can apply that to the oxygen gas, because that's oxygen in its natural state. It's a diatomic element. Then you know that when oxygen and hydrogen are present in compounds, oxygen has the oxidation number -2, and hydrogen has the oxidation number of +1. We have water here, and we can assign those numbers then. The oxygen has -2, each hydrogen has a +1, and we have 2 of them. And in this carbon dioxide, the oxygen, we have 2 oxygens, each has a -2. And in the methane, you have hydrogen, so that's 4 hydrogens, each with the oxidation number of +1. All right. Then you know that the sum of oxidation numbers in an uncharged compound is 0. Therefore, the oxidation number for this carbon must be -4, because it's connected to +4. So the sum of this is 0. Everything is fitting nicely. And let's look at the carbon in this molecule over here. Here we have a total of -4 as in oxidation numbers. To cancel that out, we need a +4. And note that these aren't charges, right? These are oxidation numbers, which is why we have the plus and minus in front of the number instead of after, which then indicates a charge. All right, perfect. We've now assigned oxidation numbers for every single atom here in this chemical reaction. Let's look here. Carbon goes from a -4 in oxidation number to a +4. That's an increase in oxidation number. Therefore, this will be what's oxidized. So the carbon in this reaction is oxidized. The oxygen goes from 0 to -2, every single oxygen atom. So this will correspond to a reduction, following our rules. And now I want you to think a little bit. How many electrons are transferred here? So think about this for a while, pause the video, and then I'll come back and we'll see if you guessed correctly. Okay? So pause your video now. Okay. So, how many electrons are transferred in this reaction? Well, first and foremost, I've removed all the other oxidation numbers, so we just keep track of the carbon for now. Carbon changes from -4 to +4. That's a large difference, right? Does that mean that we have 8 electrons being transferred? When we looked at the metals and non-metals reacting before, we had an equal number of electrons as the change in charge. So when iron turned from iron to Fe2+, then that corresponded to losing 2 electrons, right? Does this follow the same principle? Let's draw the Lewis structures of methane and carbon dioxide and see what we have. That's the Lewis structure for methane. In this case, 2 shared electrons, like this, corresponds to a single bond. So it's a carbon with 4 single bonds to 4 hydrogens, like so. And this carbon is going to change from being bonded to these hydrogens to be bonded like this with a couple of oxygen atoms in carbon dioxide, in this case. So let's look at the electrons here. For the methane, carbon has access to 4 valence electrons, 1 per single bond, if you remember. So you can sort of split every one of these bonds in half, and then half will go to the atom on one side and half will go to the atom on the other side. So the innermost electrons here belong to the carbon. So this carbon has access to 4 valence electrons of its own, right? And then of course it shares, so it reaches a noble gas configuration here. And that's why we have covalent bonding. But only 4 of the electrons are its own. Over here, carbon also has access to only 4 valence electrons of its own, right? It can, since it shares, it gets access to 8, therefore reaching a noble gas configuration. But only the innermost electrons here actually belong to the carbon. So these 2 and these 2. So 2 per double bond. So carbon will have 4 valence electrons belonging to it before, and carbon will have 4 valence electrons belonging to it afterwards. It does not turn into any type of ion, so no electrons are transferred here. So we only have we can say a rearrangement of the electrons, but we don't have any ions formed here. But that complicates things, right? Because our definition for reduction before was gain of electrons, and our definition of oxidation from before was loss of electrons. But in this case, carbon neither loses nor gains electrons. So that's why we need to do this. We need to, I need to give you guys a better definition for what is a redox reaction. A redox reaction is a reaction where the oxidation numbers, and they're also called oxidation states, but when the oxidation numbers of atoms are changed, then we have redox reactions. In this example, the carbon atoms were oxidized, but no electrons were changed. We still have the same number before and afterwards. And the oxygen atoms were reduced, but they didn't gain extra electrons or lose extra electrons. It's just that they bonded differently. So rearrangement of the electrons, but still the same number actually belonging to every single atom here. When you see a change in the charge of an atom, for example, when an atom forms an ion, or when an ion forms an atom, then you know that the number of electrons change, but not otherwise. So now you have a new definition for redox reactions and what they mean, using the new concept of oxidation numbers. Oxidation numbers are used not only to figure out what's oxidized and reduced, they're also used, for example, and I will show you this in a later video, they're used to balance complicated equations or reaction formulae. But they're also used in a more conventional way or more everyday way, and that is that they're used when we name metal ions. And as a consequence of naming metal ions, we also need to name ionic compounds. So we're going to go through this a little bit as well. Those of you who were my students did an experiment where we didn't know if the copper formed either +1 ions or +2 ions. Copper is a transition metal, therefore it can form ions with a varying charge. So there's no nice clear rules that it's always +1 or always +2 here. So then we did an experiment and we found out that it was Cu1+, if I recall. But nevertheless, same atom forms different types of ions. We need a way to account for this in names. So we usually refer to these ions by their oxidation numbers. So when you have a copper 1+, it's named copper 1, like this, with a Roman numeral, Roman number, in a parenthesis after the name copper. And Cu2+ is called copper 2, which I now fixed, so no space in here in between. So copper 2+ is named copper 2. Note that we use Roman numerals, so Roman numbers. This is very useful when we name ionic compounds, when they contain these transition metals. So let's look at this. If we know the name, we know the charge of the cation, and then we know the empirical formula of the ionic compound in turn. So let's look at how we can use the name to figure out the formula of a metal compound, an ionic compound. For example, here you have iron 2 sulfate. And that's how you will, for example, find the name of it if you Google and find it on Wikipedia. Okay, iron 2 sulfate. That means that we have an iron 2 plus ion, because we have written 2 here as the oxidation number. An oxidation number and charge of ions, they're the same. Okay, so we know it's an iron 2 plus ion. And the sulfate ion you know by heart, it's SO4 minus. The overall charge for the compound is 0. So then we need, for every 2 plus ion, we need a 2 minus ion. So it's 1 to 1 here. So it's iron sulfate. So we went from name to formula. But we can also buy iron 3 sulfate if we want to. Well, that means that we have iron 3 plus ions. We can read that from the oxidation number in the name. We still combine them with sulfate ions, which we know the formula of and the charge of. And then we need to combine these so that the overall charge is 0. Then we need to find the lowest common denominator. We need 2 iron atoms for every 3 sulfate ion. So 2 iron ions for every 3 sulfate ions. Because this will be, each of these will have a plus 3 charge. 2 of those, that's a total of plus 6. Each one of these sulfate ions has a minus 2. Times 3, then we have a total of minus 6, so that will cancel out. And that's how you use the name to find the formula, as long as you know oxidation numbers. So, what is the formula for chromium 3 nitrate? I'd like you to pause the video and solve this on your own, and then I will show you the formula before we finish up the video today. So pause your video and solve. All right, here's your answer. Chromium is a 3 plus based on the name here. Then each nitrate will have a minus 1, so then you need 3 of those. So that's the end of this video. I hope you learned a lot from this. You have a better definition for what a redox reaction is. You can understand what those numbers you find when you, for example, Google a chemical actually mean. And you can figure out quite a few things about chemical reactions. Thank you for your attention, and I will see you in another chemical video.